Hello, hello. This is Jonathan Doolin, and I am, or I have been, reading a text called "Planetary Core and Surface Temperatures" by Douglas Cotton, uh, published in SSRN Electronic Journal, and 2013. Let's see. This is kind of my reaction to it, but have been kind of taking a momentary break from the reading because there are a couple of concepts that I want to explore. One of them is called the barometric formula, and I feel like the concept here is a little bit incomplete, but I'm going to try to describe it for a second. So I said it was incomplete, but I want to show you how I would complete it. Although when I show you how to complete it, I have not necessarily completely finished the problem. I'm just trying to give the direction to it. So the first thing is we're going to take the ideal gas law and we're going to put it in this form: P equals N over V times RT. And then this N over V is called the molar density, and that is measured in moles per meter cubed. But I want to actually have something in the form of kilograms per meter cubed. And so in order to get from that to that, I need to multiply by kilograms per mole. Put moles on the bottom, put kilograms on the top, or moles per kilo. What is that? So what I'm going to write is this is N over V. Kilograms per mole I'm going to write as mu, which is the molar mass of a substance, and that will give us equal to kilograms per meter cubed. I'm going to call that symbol rho. So I've got N over V, but I want to express it in terms of rho and mu, so I'm going to replace this N over V with rho over mu. Rho over mu RT equals our pressure. And then, now that I've got this, I am going to say that the molar mass of a substance is a constant, and R, the ideal gas constant, is a constant. So I'm going to express this as P equals R over mu, and then I'm going to give the variables, which is the density of the gas times the temperature. So the density of the gas and the temperature can vary. And then I'm going to, we've got a function basically of three variables, and we can add a fourth variable of height. And this is going to be dz, dp dz is going to be R over mu times T d rho dz, and this is partial derivative actually, d rho dz, where T is constant, plus rho del T del z, where rho is constant. And that is a differential formula for that. Okay, so now the reason the thing that I was just looking at calculates this, the d rho dz, where t is equal to constant. T is a constant. Actually, no, it calculates this, dp dz. It calculates del p del z, where z is a constant. So actually, I should reorder this equation, because what is actually calculated here is del p del z, where temperature is assumed to be a constant. So I think what we ought to do, if we want to use this expression, then we need to re-express what I've just given in terms of pressure and temperature. So we're going to have density on one side, pressure and temperature on the other. So what will that look like? Okay, that's going to look like this. density equals mu over r, this is our constant, times p over t. Then when we do the derivative of that, okay, this is what I got. When I take the derivative of this formula here, I'll get mu over r, our constant, put it out in front, and then we'll take 1 over t times del p del z, and then times p times del t inverse del z. But when I take del t inverse del z, I get negative t to the negative 2, and then I'll take del t del z. Chain rule right there. So I think this is what we would have. Okay, so what they have for del p del z is actually calculated in this article from Hyperphysics. It's expressed as delta p equals negative rho g delta h. So I will just say del p del z equals negative rho g. And I'm going to declare that that is going to be plugged into there for del p del z. That's going to just be negative rho g. As you go up in the atmosphere, the pressure is going down at that rate. And you can see the reasoning for it right there, based on the weight of the air. But they are calculating things as though we have a constant temperature. I do not want to use a constant temperature. I want to give some kind of reasoning for why the temperature would be different. So that's why I have this del T del Z here. This del T del Z is going to be, well, let me go into some of the reasoning that I went through this morning already. Question 1, is there any principle by which to determine the kinetic energy of molecules as a function of height? And occurred to me that I said, imagine a diatomic molecule. Actually, I had already asked this question too. Will said principle affect the total internal energy or the linear kinetic energy? And I had not answered that yet, but I came over here and started thinking in terms of imagining a diatomic molecule falling. It increases in linear kinetic energy, then collides with something, setting the molecule into spinning. And I felt like when the molecule is sent into spinning here at the bottom, then that means that gravitational potential energy that it gains from falling is converted partially into linear kinetic energy, but it also should be converted into vibrational kinetic energy and rotational kinetic energy. So that means that what I'm applying here is that we're going to say that, let's see, I don't know if I said it very well right here. I eventually come to it, that the kinetic energy up like at some top layer is 0, but down at the bottom layer it's a rho g h. I ended up calling this h sub z minus h to be the h sub z represents the layer where there is 0 energy, and h represents the layer where the variable. Okay, so let's check this derivation. Basically, we start with 2 over the degrees of freedom times u equals nRT. This is, and then I replace 2 over degrees of freedom with r over the specific heat at constant volume. So that is essentially a property of the gas, the specific heat at constant volume. And then I replaced U with the internal energy, which is rho g h sub z minus h. So as h decreases, the internal energy of the gas increases, and it's proportional to the density of the gas times gravity. Then over here on this side, I use that formula that I put over here, that moles per meter cubed times kilograms per mole equals kilograms per meter cubed. So divide both sides by mu, and you have moles per meter cubed equals kilograms per meter cubed divided by kilograms per mole. Alright, so now we have rho over mu RT on this side. We've got this expression for energy on the other side, and we want to solve this for T. So basically this next step solves for T. So we got, I've got some variables that are presented twice. R rho is on both the top and the bottom, R rho. So those both cancel out by the end. We've also got that this is a constant minus h. So when we take the derivative with respect to h, the constant part goes away, and we are left with, okay, so one thing to fix was to add that negative sign there. I also prettied it up a little bit so that instead of going to del t del h here, I just canceled out r rho, and left c sub v and the other variables that were not repeated. So yeah, it looks like del t del h is negative mu sub g over c sub v. And it seems, okay, this method, I was hoping that I'd get things in terms that would be simple, but it looks like I did not isolate in terms of pressure. The pressure, oh wait, is that a P? Yes, it is a P. I'll tell you why I'm concerned about this, is because I kind of wanted my del rho del z to come out neatly in terms of not in variables, but in terms of constants. That would have been really nice. Before I proceed in this direction, let me show you what I got when I left it in this form here, with everything on top. Instead of putting temperature on the bottom, I left everything on top. And that looked like this. When I took dp dz, well, I have p equals r over mu rho t. So when I take dp dz, I get r over mu, those are our constants, times t del rho del z plus rho del t del z. Del rho del z, we don't have anything for del rho del z, so I just left that alone. But we did have something for dp dz. Of course, the trouble is this isn't dp dz. That's yeah, that would be del p del z, not dp dz. That wouldn't be the total derivative, so I'm not sure how well that'd work. So I don't feel confident in this. I don't feel confident in this step because we didn't calculate dp dz as negative g rho. We calculated del p del z is negative g rho. So I don't feel quite as confident in this derivation. Okay, so here is the description that I've just talked my way through. I want to check for any errors in math or logic. So we got density is equal to mu over r times, or is that mu over r? Yeah, it looks weird. PV equals nRT, n over v is here, and then we're making that rho over mu, and so that mu over r comes up to the other side. and then T goes to the bottom. So yeah, that's mu over R, pressure over time, pressure over temperature. And then del rho, the total derivative of rho with respect to z is going to consist of the addition of these two partial derivatives, which is the t to the negative 2 comes out. And then what I need to do here, I feel pretty confident on this part that del p del z, where t is constant, is negative rho g. But what I want to do is go through my reasoning over here, del t del z, I want to make sure that the concept that I'm thinking of is consistent with the pressure being constant. So here was the reasoning I used, imagining a diatomic molecule following. It increases its linear kinetic energy downward, then collides, setting the molecule into spinning. It could spin, it could be moving up and down. But in this conceptualization, was the pressure constant? Okay, to find the molecular description of pressure, basically it's a force divided by area, and for the force you're going to have all those particles running into the wall of the chamber. So it's the sum of all of those delta mv's, and I think mass times velocity over time gives you, mass times acceleration, or force. So that would be mv over delta mv over delta t, and the area down there. So this would be the pressure of things, and what I think I want to think about is a top and bottom wall of the chamber. And what's going on is that the molecules are down here, striking with a delta V of, well, let's just make up some numbers for a second. Let's say this guy comes down, hits at 1 meter per second, bounces back at 1 meter per second. Then he slows down to 0.9 meters per second, and he bounces off this surface at 0.9 meters per second. Okay, so the delta V here was 2 meters per second, and the delta V up here was 1.8 meters per second. Same area, same delta T, same mass, but the delta V is different. So we cannot say that pressure equals constant in this. So we have to ask a different question, and that question is whether, well, first of all, just because p equals constant, p is not equal to constant, does not mean this isn't a partial derivative. What it means is that it's a path derivative where p has some special status. And that special status, that path derivative, is basically, we're going to ask whether that special status is independent of this special status, or if it's dependent on this special status, or if it is actually the same as this special status. Because we might be changing this to an equality. What we might end up doing is saying that this is equal to this, and that is equal to that. If that's the case, then we've got a triple equality. And I think it's time to go back to see whether this t equals constant was based on actually t being constant, or if I made some error, I think I made an error based on an error that the person here made. I saw this equation, rho equals mp over kt, and I thought, well, because they are plugging it in and integrating as though t were a constant, that would mean that the differential as a constant implies a constant t. But I don't think it does. I don't think it does. Okay, so let me try to state this again in the form of a question. We have the pressure is equal to this quantity, r over mu times rho t. And the question is whether the cause of if we assume that the pressure varies with height, which it does, should we assume that part of that variation of pressure with height is due to a variation of density with height, and another part is due to a variation of temperature with height? Or would those two things be independent? If they're independent, then this would be the expression. And same thing down here. The density definitely changes with height. Should we assume then that density can be broken down into two independent parts? One cause is how the pressure varies with height, and the other due to how the temperature varies with height? Or are these two things actually the same phenomenon, how the pressure varies with height and the temperature varies with height? In which case, instead of this being a minus sign in here, I would like to posit a claim about the ordinary differentials that instead of that minus sign, we put an equal sign in there. And then we'll have the variation of density with height is equal to mu over RT, or negative mu rho g over RT, but it is also equal to negative mu pt squared. I guess, is this come out to be a positive? That's weird. Well, at this point, after looking at these and seeing just one little detail about it, one of them comes out to be negative and the other one comes out to be positive. So we can't just say that those things are equal. Of course, notwithstanding a mathematical error that I've made somewhere. But I don't see a mathematical error. Okay, I want to come back to this statement here. I said in the third step I have put ordinary derivative dp dz equals negative g rho, but I don't feel comfortable with that assumption, as it should be partial derivative del p del z t equals constant equals negative g rho. I think I'm going to go back on this. I think it actually should be ordinary derivative dp dz equals negative g rho. This is, we should actually expect that for any given height z, that the pressure will change in a manner proportion with the gravitational field at that height times the density at that height. And that formula will be independent of temperature and pressure. It will be independent of temperature and, yeah, pressure. What was I saying? Independent of temperature. What I don't feel comfortable with is this solution here, where this is calculated based on the height, and what's actually done is that this thing is being integrated where t is being assumed held constant. So I still do need to figure out how it's going to change when t changes.